happy to have Hofie Hannesdottir from the IAS telling us about analytic properties of scattering amplitudes.
All right, thanks, Monica, and thanks a lot for the invitation to come here. I'm around today and tomorrow as well, so if you have any questions after the talk, feel free to find me. So I'm going to tell you about, as the title says, analytic properties of scattering amplitudes very broadly. And one thing is that I'm not going to go into many technical details. I'm rather going to tell you about some results that we've been working on. So I wanted to say way in the beginning that if you have some questions about the details that go into the different derivations, also feel free to either ask or come find me later. All right, so the question that we're very broadly trying to ask is how can we understand fundamental particles in our universe? So I work on scattering amplitudes, which are interesting to me because they provide a bridge between theory and experiments, and as we'll see, they also have many nice physical and mathematical properties. So we're going to talk about these amplitudes for measuring some final states given some initial states, and of course these are the crucial observables that we use in particle colliders. But in particular, we know that in colliders, particles collide with real energies and real momenta. But what we're going to do in this talk is that we're going to take the scattering amplitude as a function of the Mandelstam invariance. Here, for example, in a 2-to-2 scattering process, we could have a function of S and T. And we're going to uplift it to the complex plane. So we're going to ask what happens if we don't restrict ourselves to the physical setup of real energies and momenta, but rather look at the full complex plane. And then we're going to ask what do physical principles imply for complexified scattering amplitudes, and we're going to see many new surprises. And let me also mention way in the beginning some asymptotic goals, some goals that I have in mind very broadly for this research program. And actually the reason that I got into this in the first place, the motivation was from collider physics amplitudes, where we know that there is some factorization going on due to scale separation. And the question is, can we directly probe the analyticity properties of what's called the hard function, or just about the short distance scattering? So very little is known about that right now, and that's a question that's always at the back of my mind when I work on this. But we're actually not going to look into that today, but hopefully, yeah, if you have some ideas yeah, I wanted to tell you that that's something that I've been thinking about for a long time. Another motivation is a recent connection between scattering amplitudes and observables in gravity in classical GR. And for example, if we compute waveforms that we'll talk about later in this talk, there are questions about, for example, if we can relate scattering waveforms to bound waveforms. So basically when black holes merge versus when they scatter off each other, if they're related by some analytic continuation. A third motivational example that I wanted to mention are energy correlators, which are observables that measure deposits of energy in a detector. And the interesting thing is that they have many analogous properties to scattering amplitudes. And in particular, it's been shown that the 3-point energy correlator can literally be written as a sum of scattering amplitudes, as like a triangle and box scattering amplitudes. So one question is, can we use similar methods to what I'll be talking about today to learn about different observables, not just scattering amplitudes? But the goals for this talk are the following things. First, we're going to show how to use more physics input to compute scattering amplitudes and other observables via this connection to their complex properties. And then we're also going to show how to use analytic continuations in the complex plane to relate different observables to one another. So here is the outline. We're going to start talking broadly about analyticity properties of scattering amplitudes in part 1. Then in part 2, we're going to use some of those analyticity properties to show how to compute a Feynman diagram in a completely new way, just using these analyticity properties and nothing else. And then in the third part, we're going to get to how to relate different observables by doing an analytic continuation. So let's start with point 1, where we're going to talk about analyticity properties of scattering amplitudes. So in recent years, we've actually learned a lot about the analytic structure of scattering amplitudes in particular in perturbation theory. So in perturbation theory, what we can do is that we can take our integrals and our Feynman integrals or our integrals for our scattering amplitudes, and we can analyze their properties generally. So we're going to talk about these three things: singularities of amplitudes, sequential discontinuities, and limiting behavior. But in recent years, we also have new and powerful mathematical tools, and one of them is called the symbol. And if you've not seen the symbol before, I'm going to explain very briefly what it corresponds to. What the symbol does is that it kind of packages information about polylogarithmic functions in a very nice way. So for example, let's say we have this dialogue. The dialogue is defined as an integral over two poles. One is x2 equals 0, the other one is x1 equals 1. And the other defining feature is that you can see that the integration bounds have this property that the inner integration ends at its upper limit is the next integration variables.
It's the same operation that to organize this transcendentality?
Yeah, exactly. So basically what the symbol does is that it keeps the information about the poles. So it keeps the information that we're doing in iterated integrals here over the pole at 1 and the pole at 0. So that's what the second expression is capturing. It's 1 minus z because there is a pole at 1, and z because there is a pole at 0. And in terms of the analytic structure, what it means is that it's precisely keeping track of the branch cuts of the function. So if you remember, a branch cut of a dialogue starts at z equals 1 and runs along the positive real axis. But if we take a discontinuity across that branch cut, what we get is a logarithm that has a branch point at 0. So the symbol precisely tells us that we have a discontinuity starting at z equals 1. And if we take the discontinuity across the branch cut, we have a new branch cut starting at z equals 0. So that's what this arrow is saying as well. Now what I'm drawing here are the imaginary parts in the complex plane for the dialogue and then the log, because the log is precisely the discontinuity of the dialogue. What's nice about the symbol is that if you worked with polylogarithmic expressions, you might have found yourself on this webpage, I certainly have, where we have some formulas for identities of the polylog. But the nice thing is that the symbol completely trivializes all these identities. They just become very simple algebraic manipulations. So we never have to look in this table again. So what this was used for around 15 years ago is that there was this computation of the two-loop MHV remainder function in n equals 4 super-Yang Mills that took 17 pages to just display the result of. I'm just showing the first three here. But using the symbol, this paper from 2010 by Goncharov et al. Was able to shorten the answer from 70 pages to these 2 lines. And so that's kind of what it buys us. It trivializes all these identities, so it's much, much easier to work with. It's not keeping any redundant information. So that's what we're going to use to our advantage. What we're going to do is that we're going to talk about physics constraints. We're going to derive consequences of causality, unitarity, and locality from the integral form of scattering amplitudes. Then we're going to use the symbol from the math side, and we're going to impose constraints on the symbol. And because we trivialize the identities, then that's a much, much better handle than using the functional forms. And then we're going to write an ansatz and iteratively apply constraints until we uniquely fix the answer. So that's the idea. Is the idea clear before we go on? So that's the idea. So let's revisit these 3 components that I talked about: singularities, sequential discontinuities, and limiting behavior. So the first thing to know is that singularities of scattering amplitudes are at classical configurations. And this is actually often taken really as an axiom non-perturbatively, but in perturbation theory you can work this out. And what does it mean? It means that if we have a Feynman diagram like this one, where we have 2 particles, the red and blue one coming in, and there's a bubble diagram, and we assume that the internal particles has a mass, capital M, and then there are 2 particles going out. The idea is that if the center of mass energy squared is precisely the point at which we can produce the two particles in the rest frame, then that's a classical configuration at which this process can happen. So quantum mechanically, we have interference between these are basically plane waves that can interfere in non-trivial ways, but classically there's just this one point at which this process can happen. And that means that the scattering amplitude is enhanced. It's enhanced at classical configurations. So that's why in the quantum theory we can get singularities. So let me show you a movie of these particles. If we're right at this point, where their energy is precisely big enough so that we can make the two new particles, each of mass capital M in the rest frame, then basically what can happen is that they can recombine again to the red and blue ball. So this is a process that can happen fully classically, precisely at this point. But if the energy is lower or higher, we still have to include this as a Feynman diagram, even though it's not like a classical process. On the right, we have a different diagram, a triangle diagram. Let me maybe stop the movie. And what we've done is that we basically plotted where the singularity is, where this process can happen classically, for the scattering angle as a function of the center of mass energy. Excuse me. So the idea here is that the kaon can physically split into two pions. One of them, the pi 0, classically hits a proton sometime later and scatters off of it, and then the pi 0 later recombines with the pi plus to form an outgoing kaon again. So this is something you can just compute. What are the values of the classical momenta for which this can occur? And you would get this curve. You don't need any quantum field theory or Feynman diagrams here. Okay. So for any Feynman integral, you might have learned at some point that what you have to do to find these configurations is to solve the Landau equations. So here I've written down the Feynman integral for the bubble. We have some loop momentum L, and we have two propagators of mass M1 and M2. So the first thing you might think is that, oh, we get singularities whenever we have poles of this integral, or poles of the integrand. So that might be our first guess. Are there singularities where L squared is equal to M1 squared, excuse me, and P minus L squared is equal to M2 squared? That's true. There is a singularity, but it's not a sufficient condition. We also need the integration contour to be pinched to have a singularity. Sorry. And more generally, what we can do is that we can use Feynman parameters to combine the different denominators, and then we'll have to work out basically what are the conditions for the integrand to have a singularity, but also for the integration contour to be either at an endpoint or to be pinched. And that's how we get the Landau equations. So either the alphas are 0, or the particle is on shell, and around every loop you need alpha L to be 0, the sum over the loop. So let's do this for the bubble integral that we had before. We plug in the on-shell conditions. We're supposed to solve for the classical configurations. So we put the particles on shell. And then we also have this kind of Kirchhoff condition guaranteeing that this can be a space-time process, that this can be a classical space-time process. And now we basically have three equations for two unknowns. So we get this extra constraints on the external kinematics. So we get an extra constraint, and it tells us precisely that the center of mass energy squared is this M1 plus M2 squared, or the other condition, which is M1 minus M2 squared, which is a bit more foreign. It's not really the point at which we can create the two particles, but it's almost like if one of them was going backward in time. So if you've heard about the physical sheet, then this singularity would be on the physical sheet, and the other one would only be there after analytic continuation. All right, and now we can start making crazier diagrams, like this one. And here is a plot as a function of s and t, the incoming center of mass squared and the momentum transfer t, just in like a real slice. And the blue and yellow curves are all different singularities of this diagram. So they can get pretty wild. But the nice thing is that we have actually very recent work from last year and this year on how to explicitly solve the Landau equations, and some software for doing that. One thing that's going to be important for us is the following kind of geometric reinterpretation of the Landau equation. Sorry, can actually someone get me hot water or something? Because I was just erasing chalk and then sometimes that.
Hot water?
Yeah, just that would be great.
Great.
Thanks so much. Yeah, so this geometric picture is going to be important for us a little bit later. So we can view the Landau equations as just algebraic equations that we want to solve. But what's going to be really useful for us is to instead view them in this topological manner. So this is kind of an abstract picture of what's going on, so let's try to unpack it. We're again showing this just for the bubble diagram, the simplest diagram, although this picture generalizes. And we have some mass m1 and m2 and internal momentum q1 and q2. So now let's imagine that in the space of the loop momenta and external kinematics, so in the space of S and the loop momenta, which is kind of the 3D space in this picture, then we have these on-shell conditions that generically would intersect in 2 points, or 0 points. So it would be either basically the picture over here, where we have the blue circle and the red circle not touching each other at all, or the picture up here where they intersect at exactly 2 points. But then there are special points in the kinematic space where they just touch at 1 point. And those points are precisely where we have solutions to the Landau equations. So we can now reformulate the Landau equations in terms of this topological property, that if we have these on-shell surfaces, or these on-shell constraints, we get singularities precisely when basically the rank of the projection map from this loop momentum space to the external variable space, yeah, when that map drops rank. And you can show mathematically, and it was done in this paper from a long time ago, that these formulations are completely equivalent. You land on the same Landau equations. So remember this picture, it's going to show up again. We'll come back to this point. All right, so that was part A. Thank you so much, I appreciate it. Are there any questions about that before we go on?
You explained the idea of the, you explain again that idea of the previous slide?
Yeah? All right, so the idea is that this is a schematic picture because we don't have enough dimensions to draw this in. But the idea is that the blue surface is the space of external variables. So it could be, in this case, it would just be the complex space of S. More generally, it could be S and T and all the Mandel-Sum invariants that you have. And then if we uplift that to the higher space, you can imagine that kind of the y or the z-axis in this plot is what I wanted to say, is the loop momentum. And so what happens here is that in this full space of loop momenta and external kinematics, we have these on-shell surfaces, kind of the constraints given by q squared equals m squared for every particle. Yeah, and then the idea is that we have singularities precisely when the topological properties change for this on-shell space. Any more questions? All right, then we're going to go to part B, which is sequential discontinuities. So let me first try to convince you why sequential discontinuities can be useful. And we're again going to do the example of the dialogue, which is a function that arises all the time in computations of scattering amplitudes. So for example, this triangle diagram where the internal particles are massless and the external particles have some kinematic invariance p1 squared, p2 squared, and p3 squared. This amplitude can be written literally as a dialog plus some logs, where these ZZ bar variables are given in terms of the Mandelstam's as is written up there. And as we talked about before, the dial algorithm has a branch code starting at z equals 1. So now over there on the blue picture, you see a more schematic picture of the complex z plane. But as we talked about earlier, if we take a discontinuity across the branch code, we get 2 pi I times a log. So the logarithm has a branch code for z less than 0. So the idea is that you started with a function where nothing was going on at 0. There's no discontinuity, no singularity, no anything. But after taking a discontinuity, you kind of reveal a new singularity. And again, the symbol is what makes this structure manifest. So for the Li2, the symbol of that would be minus 1 minus z times z. So here we're going to investigate constraints on consecutive symbol entries. So we're going to look at, for scattering amplitudes, what happens if we take these sequential discontinuities one by one. So physically, what's going on? The discontinuities are not the places that are classically enhanced, but rather when we can create the internal particles in the diagrams. So let's look at a movie of that, where we again have our red and blue particles. But now the center of mass energy is going to be greater than 4m squared. So they can certainly create the two particles in the loop, but classically they'll never recombine again. Quantum mechanically they will, because there is some probability for them recombining, but classically they will not. But since we could create them, it corresponds to a discontinuity in the complex plane. And on the right, we plotted the imaginary part of the bubble Feynman diagram. And you can see this discontinuity that starts at s equals 4m squared and goes off to infinity on the real axis. So the key point that we're going to use for sequential discontinuities is the following: that we can compute the discontinuity across a branch cut using the same integrand, but a new integration contour that's localized around the Landau singularity. So this is not just true for Feynman integrals, this is true more generally. But we can apply it specifically to Feynman integrals, or to scattering amplitudes. So I've written here what it corresponds to in terms of an integral where we integrate over the loop momenta from k equals 1 to capital L. We have some propagators, and we've split them basically into two different sets, C and C bar. So C is the set of cut particles, and for every particles that we want to cut or put on shell, we add a delta function. So you might recognize this as Kutkowski's formula. Or, yeah, so the discontinuity is given by putting particles on shell. But the important part is that we can rewrite this equation by using residue contours around the places where these delta functions have support. So we can work with completely the same integrand, but we have these new integration contours. So we never have to write the delta functions themselves. And that's the formulation that provides a tool for sequential discontinuities.
So what is this plus minus in the data?
Yeah, great. So physically, it means that the particles on the cut have to have positive energy flow. Mathematically, it means that basically these polynomials, q squared minus m squared, have two roots, and we're picking out one of them. The singularity picks out one of the roots. So in terms of the on-shell surfaces that we had before, there will be two branches, and we're just saying it's this branch of it's this root that takes part in the singularity. So that's all cryptically represented by this little circle where we can
But since
capture
everything is analytically extended now, so what is the criterion to pick up one and not the other?
Yeah, so that is something that we're going to actually see in a minute, but yeah, you have to work that out more generally, absolutely. So you have to check if there is a way to get one root versus the other. So that's actually why I included the plus minus and not just the plus. So it's only for scattering amplitudes themselves, that we have this physical interpretation. If we go off in the complex plane, then we have no idea. We could have real complex positive, negative energies in here. Okay, but using this, we're able to actually derive some non-trivial results, and one of them relates to the Steinmann relations. The Steinmann relations were originally used in the 60s in axiomatic quantum field theory, and the idea was to basically restrict sequential discontinuities using causality, saying that we can't have branch cuts in channels that can't causally occur at the same time. This then got a huge revival around 10 years ago, where these relations were conjectured to hold for massless particles in n equals 4, and used to bootstrap amplitudes in n equals 4. So they're absolutely crucial for the n equals 4 bootstrap program. But more generally, we can derive a similar result basically for any Feynman integral. And the idea is that there cannot be simultaneous branch cuts when thresholds cannot occur simultaneously. So getting back to the question of the pluses and minuses, what that corresponds to is basically that if there is a sequential discontinuity, the two Landau singularities have to basically have a common solution. So I've tried to draw this here on these two diagrams. And we can look at two different situations. So this could be for a 2 to 2 amplitude as a function of s and t. And then we have the loop momentum k going in the z-axis. And what you can imagine is that at s equals 4m squared and t equals 4m squared, we have some singularities that are functions in the three-dimensional space. They would be these red and blue curves. So if we project them down to the external variable space, they would be at s equals 4m squared and t equals 4m squared. But more generally, there are some curves if we solve for the loop momenta as well. So the situation on the right picture is that, let's say we now take a discontinuity across s equals 4m squared. Then the discontinuity integral would localize kind of in a tube around the blue curve. So we can view the discontinuity as a new integral with the same integrand, but the integration contour would just be around the blue curve. If we then try to take a discontinuity corresponding to the singularity on the red curve, we'll just get 0 on this picture here. Because our integration contour is localized in a tube around the blue curve, then the red curve is something that integration contour doesn't detect at all. So this actually turns out to be very powerful. And on the left picture, that would be a case in which the s and t discontinuities are allowed, because they intersect in the right place. When we set both s and t to 0, there is an intersection of the red and blue curves. So that's one thing we can derive. Another point is more recent, from earlier this summer, where we basically used this picture of the different intersections that I told you about before. So I told you before that when the topology changes in the space, that's when we have singularities. And this was made precise last year by using the Euler characteristic of the space. And basically, if the Euler characteristic changes, if it increases or drops, that's when we can have a Landau singularity. That's when we can have a singular configuration. And then another realization is that if we take these discontinuities...
So Euler characteristic of what space? So this is always an even dimensional space, right?
So the Euler characteristic of the complex space involving, here I was doing the loop momenta. So it would be the space involving the S, or the kinematic invariance, and also the loop momenta. The paper actually did it in Feynman parameter space.
So this is a dimensional space because you are complexify
exactly.
dimensions, so...
Exactly. Okay, but then what we could use in this paper from the summer is that basically once we've taken one discontinuity, then that particle can never go back off shell. Then we're always working with this contour that encircles, that is the residue contour that encircles the singularity. So if we use if we compute the Euler characteristic for the new on-shell space, kind of demanding that that particle always stays on shell, then we get a new kind of topological constraint. We get a new Euler characteristic and a different criteria for when it can lead to a singular configuration. And this was, at least to me, surprisingly very powerful. So here I've shown an example of a diagram where we have this constraint on a discontinuity of one singularity, here given by S12, so it would be P1 plus P2 squared, plus S23, which is P2 plus P2 squared, minus here the Higgs mass plus the Z mass. And basically, no matter which sheet you're on, this singularity can never follow another one, which is in the Higgs mass squared minus 4 times mz squared. And we call this genealogical constraints, since they basically probe which discontinuities can be, I guess, children or parents of each other. So basically we found that for some two-loop diagrams, they put roughly hundreds of constraints on which discontinuities can follow each other. So the exact numbers are in our paper, but it was for, yeah, basically for some two-loop boxes, there were order 500 constraints for each diagram.
Question?
Yeah.
Can you say a little more how the Euler characteristic tells you about the Landau singularities?
Absolutely, yeah. So I think, let me think.
What feature of the Euler characteristic?
Yeah, because the Euler characteristic roughly tells us in the space how many integration contours there are. And so basically the idea is that if it changes, then the topology of the space is changing in some drastic way. So one thing that we can do is that we can draw, again for the bubble diagram, let me just do it in 2 dimensions, so that we have some K0 and K1 in terms of the loop momentum. For each of these, so the Feynman integral will be 1 over K squared minus M1 squared so these, in terms of this picture, these will be some parabolas in this space. And what happens right at this singularity here is that basically you can imagine the 2 parabolas just going to a point. So here you used to have basically a possible integration contour, but it vanishes right at the singularity. So this would be for s greater than m1 plus m2 squared. But right at the point where s is equal to m1 plus m2 squared, then the picture would look roughly like this. So you basically lost the contour here, and that's precisely what the Euler characteristic is counting. Yeah, so what's important for us is basically, as we go to these different singular configurations, do we keep all of our integration contours or not? And if we've taken a discontinuity, what we would do is basically that we would demand that some of the parabolas are still in there.
Hey, come on in. We were just wasting time.
All right. So now that we talked about sequential discontinuities, I'm very briefly going to mention point C, the limiting behavior. It's just the slides. I'm just going to tell you about it, and because we'll actually just use this result in our example. But the idea is that if we have some branch points or singularities, then we can use either the method of regions or some limits, let's say Regge limits, to work out what the expansion is around the singularity. So that again is some extra information that we can get, often with very minimal computations. All right, so that basically concludes part 1. The next thing we're going to do is that we're going to combine these different methods and compute this 2-loop diagram. But before that, are there any more questions?
Maybe just a very general question.
Yeah.
I think there are results from the 60s and results from the 2020s. So, but what's the difference in between these 2 time periods? I mean, what is the knew that the people that did the S matrix, etc. in the 60s
Yeah.
did not understand, or Landau
Right.
did not understand.
So the biggest difference, I would say, is that in the 60s they were working in axiomatic quantum field theory. So all of their results are for mass-gapped theories. So that's one thing that we're trying to get away from, that assumption, just because almost everything we compute is for massless particles. Of course, we're building on the big literature that was there, and as you saw in the citations, it's very impressive and a huge body of literature. But yeah, we were able to take it much further by basically using these also modern mathematics methods and kind of combine the two to derive these new type of results. So that's actually, yeah, I mean, I want to definitely give them a lot of credit because it's very impressive work, but it was interesting to me that we were able to actually, yeah, extend it to other cases, as I say, extend it to cases with massless particles, which is a priori a bit non-trivial because the more generic your finite integral is, the easier it is to use homological methods in many cases. So there's this kind of weird tension between the homological methods working very well for amplitudes where you have basically all the masses in the diagrams being different, wide angle scattering, etc., even though these integrate to horrible functions, or we barely even know how to integrate them, versus the cases where things are massless, when things get much more complicated on the homology side, requiring basically blow-ups everywhere, etc., but somehow the amplitudes are much simpler. So we've been trying to combine the two, and this work from earlier this summer was something where we really used both new techniques and the old techniques and combined them together. All right, so we can finally put all these constraints together and compute amplitudes. So I'm showing you here a table of what happens when we actually do that. So the first thing we do is that we, as I say, we write an ansatz for the symbol. And I've not told you about this today, but there is a way for us to know, or at least conjecture, that the symbol should have 4 letters for this 2 loop diagrams. It's basically, there's an upper bound of loops times dimensions over 2. So we want to do this in 4 space-time dimensions at 2 loops. It's 4 times 2 over 2. So that's what we start with. Sequences of 4 letters. And then we start with 21,000 terms. The next thing we do, we almost get for free from math. We basically impose that partial derivatives commute.
So it is the letters in which alphabet?
I'll show you those in a second.
If it's an alphabet with a single letter, there's only one signature.
There would be only one term, exactly. So here I show the letters, so we have 12 letters. We'll get to that in a second. 12 different singularities, basically. All right. So just this math constraint that we have to be able to actually write this as a function, meaning that as we integrate up, we can't have a dependence on the path, then we get down to 7,000 terms, so that's already great. The next thing we use is Galois symmetry, which is a fancy word for saying that if we have a quadratic equation, and there is no way for favoring the square root over the minus square root, we have to symmetrize over both. So that gets us down to around 900. The next thing we do is that we use that the discontinuities of the scattering amplitude, so the first discontinuity we take, has to be at physical branch points. That gets us down to 160. Then we have that the limit as s goes to 0 should be vanishing, which is basically related to the fact that there's no physical singularity at s equals 0. Then we use the genealogical constraints that I just told you about. Again, we use algebraic alpha-positive thresholds, which is more or less the same point as the physical branch cuts. And the last thing we use is a threshold expansion in T. Before I show you the results, let me show you how we actually form the letters. So the singularities of this are at s equals 4m squared and t equals 4m squared. So the thick particle has mass m. So the physical singularities are when the two incoming particles are precisely at 4m squared. Same if you go in the t channel, because the dash particle is massless. Then we have some other singularities at s equals 0, t equals 0, and s plus t equals 0, which are the singularities that are not physical. And then this last one, st plus 4sm squared plus 4tm squared equals 0, is sometimes called the box singularity. It's basically the singularity from putting all the particles on shell. And then we can compute the prefactor by putting all the particles on shell. And then we have this 4-term symbol, and the c's are initially these 20-something thousand undetermined coefficients. And the way that we form these different letters, these different possible poles out of these singularities, is that we basically we can always put a letter as a singularity, but then we have to form these square roots and combinations of square roots as well. So basically we can have logarithmic singularities, which are written out in this column here, or we can have square root singularities. And we have to take our set of lambda singularities and combine them in all different ways. That's how we get this 12 letters, but it actually turns out that 3 of them do not appear in the final answer. But we did not impose that, we just formed everything we could form, and then turned the cranks, and these turned out to vanish, or not be there.
So the question, you had less logarithmic singularity than the other ones, right? Substantially less.
What do you mean?
No, because when you saw
Yeah.
something surprising of your procedure is that if you want the less, before. You say all the steps you do, the one that reduces the less is the limiting behavior so the physical singularities. Can you explain why these physical logarithmic branch cuts, they look like, they don't do much, right? So all these steps like reduce the thing in one order of magnitude, from 20,000 to 7,000 to 800 and then this physical singularity thing just do from 161 to 100. So why?
So you think these don't give us many constraints?
Yeah,
That's what you mean?
why?
Honestly, that's still a big open question. And it's the same in the n equals 4 bootstrap program.
See, because it's, when you see this list,
Yeah. I mean, first of all, we could have done this in different orders and we would have gotten different numbers. What was important for us was to get down to 1.
Yeah.
But it's actually interesting, once you start playing with this, sometimes you can work very hard mathematically to derive a constraint, and then it gets you down by maybe 1, it eliminates 1 term or something.
I see that. Okay.
And sometimes you get,
That's why.
sometimes you get very far, and it's really not known what it is precisely that gets us far and what it is that's not. So that's something that would definitely be interesting to understand better.
Was it granted that you were gonna get an answer, or is it a miracle of this integral?
So it's always guaranteed if you derive enough constraints that you can get the answer. So basically just imagine that you take every branch point, imagine you were infinitely powerful, you would just compute the expansion around every single branch point to all orders, then you would definitely know the answer. However, what's non-trivial about this to me is that we have to check how much work goes into deriving the constraints versus how much work goes into computing the full amplitude. And here, this is actually, first of all, what I like is that many of these are physically motivated. So we use actually the physics information to compute this. And second of all, many of these are very, very easy to derive, and even general results. There is this tension between, as I said, you can always get the answer, but if it's way too much work, then you're not gaining anything. But here I would say we definitely
In principle, it's algorithmic. You apply this technique, you get all the singularities, and then by complex analysis,
Yeah. If you know that it's full logarithmic, then there is a finite number of terms to begin with. So in principle, you can always, if you derive 21,000 constraints, then you're done. Yeah. All right, so here's the answer. Maybe it's not so illuminating, except it's interesting how simple it is, I guess. But this is written in terms of the letters that we had before. And there are some minus signs between the terms, but otherwise no numerical factors, which could have been there, but turns out they're not here. But this is the unique answer that satisfies all of the constraints that we saw before.
Ask, what does the point A,
Yeah.
physical logarithmic branches, what
Yeah.
does it mean physical? It means that it's physical in the external momenta or
Yeah.
physical in the sense that inside you have on-shell particles?
It's
So-
physical in the sense that inside you have physical on-shell particles that propagate with positive energy.
I see. But the ST could be in the complex plane. They don't need to correspond. The external
Yeah,
SNT could be.
In principle, yes, but it turns out that, yeah, you can realize this with physical momenta as well.
So there are no anomalous thresholds in this field.
So there are anomalous thresholds. In this case, the anomalous threshold would be this one, st plus 4m sm squared plus 4tm squared equals 0. And they can be physical or non-physical. And it just depends on what type of diagram you have and what type of kinematic configuration. So what you would do is that you would solve not just for where the singularity is, but also, as you said, can we have, basically in terms of the Feynman parameterized version, can we have positive alphas and real momenta per integral? So the physical branch cuts are the ones that we have before analytically continuing the integration contour. So we're just asking, is this on the original integration contour? All right, so for the last 10 minutes or so, I wanted to tell you about a little bit different story, which is admittedly very related to point 1, but it kind of goes back to what we talked about before, more towards axiomatic field theory and norm-perturbative constraints. So this is work from last year on analytic continuation between observables. And I was just going to remind you of this slide, because it's going to be very, very important now, that what we're doing is that we're uplifting the amplitude to become a complex function. And this story is one of the new surprises that happened. So what I'm going to be talking about is new versions of crossing symmetry. So back in the 60s, there were a lot of important results on crossing symmetry. And let me first tell you what it is. The idea is that particles should be indistinguishable from antiparticles traveling back in time. So what that means in terms of the S matrix or in terms of scattering amplitudes is basically that scattering amplitudes for two different processes should be one and the same function, meaning that they're related to each other via analytic continuation. So one example that we can do is E plus E minus to gamma gamma. And what we're asking when we're asking whether this is crossing symmetric is that if we take the positron and the photon and we switch them from being incoming to outgoing and vice versa, can we get that function for now Compton scattering, E minus gamma to E minus gamma, as an analytic continuation of what we started? And again, this was motivated by this physical idea that particles should be indistinguishable from antiparticles traveling back in time. And this was proven for 2-to-2 scattering amplitudes in axiomatic quantum field theory, so in theories with a mass gap, in these papers by Bros, Epstein, and Glasser in the 60s. The reason why we love crossing symmetry is that it allows us to use results from previous computations. So let's say we computed the left process here, E plus E minus to gamma gamma, to 10 loops, or even non-perturbatively. We had the full, complete answer. Then if we wanted the right process, then we wouldn't have to do basically anything. We would just need to analytically continue the answer we had before. We would not need to start over again and compute every loop or find the exact answer. So let me elaborate a little bit on what was worked out in the 60s. And here what we're drawing is what happens in the complex plane for 2-to-2 scattering. I've again shown this electron-positron scattering for illustration, but really this was derived in theories with a mass gap, non-perturbatively, and at fixed momentum transfer t less than 0, so we can plot it in the S complex plane. what they showed is that there could be singularities and branch cuts on the real s-axis. We basically assume that we don't know anything about what happens there. But they also showed that there could basically be singularities within this blob in the S-complex plane, but very crucially, there is some finite size of this blob, so outside of it, we can have paths of analytic continuation, and moreover, if we analytically continue the scattering amplitude, from one channel to the other, we land on the conjugated amplitude. So we're going from S greater than 0, which means that on the right side, that the electron and photon are scattering against each other, to S less than 0, which means that the momentum transfer now between...
So a very, very nice question. So it's obvious to see that the region in which you have a numerous threshold is always compact.
That's a great question, and that's the non-trivial fact about their proof. It's precisely that it's a compact region.
Okay.
And another crucial point is that, or crucial interesting point,
Because it's known that you can have non-trivial topology, like remaining core or something like that. Is it clear that it's compact?
not at all. So that's precisely the, as I say, the important point. But the other thing I wanted to tell you is that we actually don't know about any singularities within this blob. So it's also, I guess, conjectured that the upper half plane is analytic, but that no one has proven that yet in its generality.
And then that was going to be my question. Of
Yeah.
How should I think about any singularities that would appear in that blob? Is the statement that we don't know of any non-analyticity in deep in for large imaginary S, is that true just for gap theories or?
Yeah. This proof. All of the assumptions are crucial here.
Yeah.
That there is a fixed momentum transfer and then there is a masking.
Right, because I'm thinking of, for example, in the gravitational S matrix, I think we know of non-analyticities at large imaginary S. They're supposed to somehow correspond to bound states.
Yeah, so this is, as I said, this is the setup here, and this is the case in which it's proven. Okay, so now let's extend this to the lower half plane as well. So in the lower half plane, we kind of have the conjugate picture of what's going on. And what's crucial here is that this amplitude here would be the U channel, but actually the U channel is realized approaching from the opposite side. And the reason is that we're staying on shell, we're not giving the masses any imaginary parts. And S plus T plus U, let me write this here. Is equal to the sum of the masses squared. So basically, since we're working at fixed T, if we solve for U, the U is equal to minus S and then minus T minus the sum of the masses squared. This can never get an imaginary part. We want U to have a positive imaginary part in the U channel. So the way to do that is to let S have a negative imaginary part. So that's why the physical U amplitude is approached from the lower half. So we have this picture, but if we analytically continue the amplitude, we land on the conjugated amplitude in the next channel. For the 2 to 2 amplitude, we can then do one more move. We could fix S and go from this U channel amplitude to the T channel amplitude, and then that would not be conjugated. So we can always get from an amplitude to an amplitude with 2 moves. So what we were looking into is what happens if we add more particles to this process. And naively, and definitely if you would have asked me 2 years ago, and asked, well, it must be the same for the 5-point amplitude, right? Because particle is the same as antiparticle going back in time. So we can just cross from S and have some move to get either S or maybe S stagger in this case. Maybe you'll see from the 3 question marks in the slide that the answer to that is actually no. That's not what happens. And let's do a simple example at tree level to illustrate why that doesn't happen. I have a little bit of a caveat there because everything at tree level is technically meromorphic. We just have poles, so there are no branch cuts. But we can work kind of in the narrow width approximation and imagine that these are distributions. So we're going to work with actually the I epsilons of the propagators and delta functions to probe what's going on. That's going to be really like a useful exercise before we go to the probe. In these diagrams here, we're actually going to take time flowing to the left. So let's see what happens if we take this S13 and we rotate it in the lower half plane at fixed S45. So this is analogous to what we did in the 2-to-2 process. But now we have the explicit expression, so we can just like look exactly what happens. And what the effect of that does is that it exchanges particles 2 and 3, basically the red particles in this diagram. All right, let's just do it. Let's just do the analytic continuation. What we land on the other side is that we pick up a minus I epsilon. So instead of landing on the conjugated amplitude, we now have this kind of mixed plus and minus I epsilon prescription. So it's not really an amplitude, it's not really a conjugated amplitude, but we can rewrite it in terms of basically the conjugated amplitude, which is maybe what we would have expected, plus this delta function term. And one thing to point out immediately is that let's say that this had only 4 particles. It was just 2-to-2 scattering. Then basically this 5 wouldn't be here. And this diagram here would just collapse, so we would be back to basically just this term here. So it's kind of a coincidence at 2-to-2 that you don't get these terms. But at higher points, you kind of start getting these mixed I epsilons. So the takeaway point from this example is that an analytic continuation, starting with the amplitude, lands us on something new. And the first key point when we investigate crossing symmetry in 2-to-3 scattering, or more or less in higher point scattering, is that we can actually make different observables out of the creation annihilation operators, A-ins and A-outs. So one thing that we can do is that we can stitch together 2 in creation operators with 2 out annihilation operators to form the scattering amplitude for 1, 2 going to 3, 4. But we can also do something different. So here, for example, I've written out the expectation value of an out operator sandwiched between a 1, 2 in state and a 4, 5 in state. So this is something that's not a scattering amplitude, it does not vanish, it's some new object. The second crucial point is that crossing symmetry naturally relates these different asymptotic observables. And again, I'm not going to go through the derivation here, but it's almost building upon the proof from the 60s and extending it to what happens for higher point particles. And what these other observables correspond to is actually, as I say, new things that we actually are computing and measuring already. So one of these things is written out here. So imagine that in this upper object, 1 and 2 are electrons, and 4 and 5 are electrons. And 3 is an operator for photons. So what this would correspond to is basically a measurement of the photon field, or a measurement of the electric field, in the background of electron scattering. So you can imagine that we take this in-state electron-electron, we evolve it with the S matrix to the future, where we measure some operator, A3. Oops. The Zoom meeting ended. I guess hopefully. Can you open it again?
Screen just, I mean, yeah, I don't know what happened. It still says it's recording.
Oh, it still says I'm sharing. Oh, sorry, it was just me. I think that...
Do you need a charger? Or...
No, I just crashed. And if we work with this in gravity and not electromagnetism, basically what happens is that we're relating scattering amplitudes to waveforms. So let me try to explain the difference between these observables. So scattering amplitudes are exclusive measurements where we scatter some particles and try to measure all of the outgoing particles. So at CERN, for example, we have as close as possible as we can to spherical detectors and really trying to get all the hits for all the different particles. The waveform instead is an in and observable. And it's the expectation value of the field. It's linear in the creation and annihilation operators because it's a field. In the background of some in-states of here black holes that will scatter with each other. So the big difference between these two observables is that in the waveform case, we're imagining that the detector measures only a small part of the phase space. So for example, we can imagine that some black holes scattered off each other somewhere in the universe, and then here on Earth, we measure a displacement in our detector. So we measure the gravitational field. And in terms of diagrams, we draw these as here there is some scattering process, and here this would be again this picture where this orange cut is kind of the t equals infinity slice where we measure the gravity. So the key result is that if we do the analytic continuation, again to change one particle from incoming to outgoing, then we don't quite land on the conjugated amplitude, but rather this in and observable, this waveform observable. And I've drawn this here in a complex variable called z. And this is a very specific path of analytic continuation that we wrote down in our paper that has the effect of exchanging the electron and proton in this case. Yeah?
And this is understood non-perturbatively or just in perturbation theory?
Yeah, great question. So the derivation is non-perturbative. However, there is a caveat to the proof. We have to assume basically that this path exists. So what we're doing is that we're saying if we can actually go far enough in the z variable so that there are no anomalous thresholds, then this is what we get. You can expand it out in perturbation theory and use it in perturbation theory. And moreover, what we were very happy with is that it also seems to work for massless particles. So that's something that's entirely non-trivial a priori from the axiomatic field theory derivation, since it assumes that everything is mass capped, and that's, as I say, kind of very built into all the proofs. But I think I have maybe on the next slide.
What happens if you change your contour? I mean, you arrive to something else that is also interesting? Or
Great question.
In the
as
sense,
well.
it's like how much design is
We don't know.
for?
Yeah, we really don't know. So we have this specific prescription with a very specific contour where we know what happens. And what I want to show you here is that we did a check for this basically for all one-loop diagrams with massless particles. And we did the check at the level of the differential equations, which means that we checked basically, all the subtopologies and all the different cuts that we can take, basically any integral in this family. And we took the specific path of analytic continuation. And if you see, so one side of this, I guess the right-hand side is, sorry, not the right-hand side, the minus and plus the cut is what we can compute explicitly. And then the other thing we did was that we took the answer in the different channel, and after doing this rotation of z, seeing that all these matrices match with each other. But what I wanted to say, to get back to the question, is that using these paths, basically we can go between different observables. So this is at 6 points. And if we exchange all different particles in different ways, then we get 3 families of things that we know how to go between with analytic continuations. We still don't know what happens if we take other paths, or if there exist paths that can get us between the different families. So basically, if we found one path that would connect any observable in 3 to any observable in 1, we would have an arrow between, and we would know how to go between all of them.
But what about something that's more basic about monogamy structure of the contours when you go around
Yeah.
singularities?
Yeah.
Yeah.
Excellent. So basically it's saying that all the observables in the same families have the same monodromy structure up to this requirement of what I previously called kind of physical branch cuts. So it's all the same function. If this observable is a dialogue, this observable is also a dialogue. But they can of course differ by an analytic continuation of the dialogue. But otherwise the monodromy structure, that's one of the interesting things, is that the monodromy structure is the same for these observables.
One thing that I don't understand in these diagrams is why the photon is attached to one of the two S. For an expectation value, shouldn't it be in the middle?
Excellent question. The reason for that, let me maybe go over here. So what we're doing is that we're measuring an expectation value of the field strength. So in electromagnetism, we would be computing some expectation value like this. And what happens is that this state here, psi, would be basically the S matrix times some in state. Same on both sides. But this operator here is linear in the fields, roughly A plus A dagger with some exponentials as well. So what we have is that if we basically act with our creation annihilation operators to create this state, then we have some A, let's say A1 dagger, A2 dagger, acting on the vacuum, S matrix, and then we have roughly A plus A dagger for the field, S dagger, and then A1 prime, A2 prime, let's say, in the vacuum over here. So basically what we're computing when we put one photon at time equals infinity attached to one S plot is that we're computing one of these terms. And then to get the observable, we have to sum over the term and the Hermitian value. But yeah, it's a great point that it's really linear in the fields. If it was quadratic in the fields, it would be something like a cross-section. It would be like the inclusive, yeah, like if you have a Higgs instead of a photon, it would be kind of the inclusive production of a Higgs. The cross-section for that.
Maybe just a couple of minutes. So.
Yeah, I'm actually done. So yeah, thanks. Yeah, let me just leave you with this conclusion slides about the three things that we talked about. But yeah, thanks for coming, and I'm happy to take more questions.
One question is that you mentioned that these methods may help relate the scattering, gravitational scattering to, say, the inspiraling. And so what kind of continuation would you need to do? Or just in energies? Or
yeah, presumably that would be a continuation in terms of the energies. So yeah, that was a kind of a open problem that I proposed in the beginning. I think that would be excellent to try to figure that out, how to relate the scattering and fast state.
Because I remember from what Swibert told me, is that there are these expansions computed by Damour using Damour's method, so brute force calculation for scattering and for inspiraling, and they can be matched to one. Two can be matched, but the matching seemed quite strange. There were some constants that changed, some Euler gammas that became other. So it didn't look just that an energy went into I energy.
Oh, that's interesting. Yeah, I thought there was some at least leading order statement about how the different observables continued into each other, but I think it's definitely still an open problem.
So these genealogical constraints that you mentioned in the second part, are you imposing like only these zeros, or there's also some positive, like you know what some of these can be after all these steps of the genealogy, after taking all these discontinuities?
Yeah, so we're not imposing anything about the physical sheet or things appearing in sequence, etc. So that's, I guess, the strength and the weakness of the genealogical constraints is that basically they tell you, because they're purely topological, So they tell you after you've taken one discontinuity, at any point after any analytic continuation, can another discontinuity appear? So that's what I was trying to, let's go back to that.
So they're all in terms of these sort of negative statements.
Yeah, it could be these negative alphas or even complex.
I mean, negative statements in that there's no discontinuity after a certain sequence.
Ah, yeah. They're a negative statement, exactly. They forbid, of course now I can't find it, yeah. They forbid basically if this is the scattering amplitude I or any other cut or basically integration contour in this space, you take this discontinuity first, it says never again can the second one appear. Exactly. So they're very much in the spirit of the Simon relations.
I just have, so you, just back to when you started with the Landau equations.
Yeah.
And then you reformulated this as being a condition on some sort of coupling map.
Yeah.
And the location of the poles were the ramification points.
Mm-hmm.
Right, and I was just wondering, is all that you get from this coupling map just the location of the poles, or is there any other physical information that this coupling map contains? Like, can you?
Yeah, you can get the physical information as well in terms of like what's on which sheet, or whether it's a physical singularity or a singularity after analytic continuation. But it basically requires keeping track of the I epsilons.
Okay.
So I didn't quite do that in this case, but did I erase? Yeah, I erased the eyelash figure. But yeah, it basically corresponds to keeping track of which exact integration contour you started with. But you can also just be agnostic to that and just look at the topology of the space, and that's how you get these kind of constraints that work on any sheet.
No more questions? Thank you again.